Greetings. My name is Alina Serhievna Venhrina, Associate Professor at the Department of Cybersecurity and Information Technologies of our university. During this semester, we will study the discipline database organization and storage together. Today's first lecture is dedicated to the absolute basics. What are data, databases, and data models? At first glance, this topic may seem purely academic, but I want to emphasize right away. In the modern IT ecosystem, there are virtually no non-trivial software products that do not rely on state persistence. Websites, mobile applications, games, banking systems, all of them rely on databases for their operation. At the same time, the real complexity lies not in simply storing data. For that, ultimately, a regular text file would suffice. The complexity lies in managing them, how to ensure integrity when data is corrupted, how to guarantee consistency when thousands of users attempt to update the same information simultaneously, and how to instantly find a single record among billions. It is important to understand that the most expensive technical mistakes in a project's lifecycle are mistakes in data architecture. Fixing logic in code is relatively easy, but a poorly chosen data model or an incorrectly designed schema at the system scaling stage is a catastrophe, the correction of which is often equivalent to rewriting the product entirely. Therefore, our goal today is to establish the key prerequisites of the discipline, starting with a clear distinction between three concepts: data, database, and DBMS. Understanding this differentiation is not an academic formality. It is the conceptual foundation of the entire industry. Here is our plan for today. First, we must agree on terminology. We will clearly distinguish three fundamental concepts: data, database, and database management system. In everyday language, these terms are often confused, but for an engineer, understanding the difference between semantics, data, structure DB, and technology, DBMS, is essential. Second, we will look at the roadmap of the design process. No one designs a complex database live immediately. This process is divided into three levels of abstraction: conceptual business idea, logical technical plan or schema, and physical, how data is actually stored on disk. Understanding this architecture is the key to data independence. Third, we will analyze in detail the first and most important level, conceptual. We will study the methodology of data description known as the ER model. It is based on three key components of any schema: entities, representing objects; attributes, defining their properties; and relationships, describing the interaction between them. Next, when we have a conceptual plan, we must choose how to implement it. And here we approach the main technological crossroads of modern times. We will compare two main paths: the classic relational SQL, which aims for integrity preservation, and the modern non-relational NoSQL, for which the main priorities are flexibility and scaling. And finally, we will take a short excursion into history. The relational model was not the first. We will look at its predecessors, hierarchical and network models, to understand exactly what problems SQL solved and why it dominated the industry for decades. So, let's start with the first and most basic concept: data. In its simplest form, these are just raw, unprocessed facts. Imagine the number 10.5 is written on a piece of paper. This is data. What does it mean? Unknown. It has no meaning or use until we provide it with context. And this context, or semantics, is the key aspect that turns data into information. Look at the example. If I add the context that 10.5 is temperature in degrees Celsius, these data instantly become information. It is quite cool outside. But if I change the context and say that it is shoe size in the UK, the same data 10.5 becomes completely different, but equally meaningful information. This is large men's footwear. This path from a simple fact to meaningful information and knowledge describes the classic model, which we will consider on the next slide. This process we just discussed, the transition from raw facts to useful information, is the first step in the classic model known as the DIKW pyramid. You see its visualization on the screen. This is the information hierarchy. At the base lies data. This is our raw fact, 10.5. When we add context, answering the question, what is this? We rise to the level of information. It is no longer just 10.5. It is, the temperature is 10.5 degrees Celsius. The next level is knowledge. It answers the question, how? How can I use this? If the temperature is 10.5 degrees Celsius, one should wear a jacket. This is already information applied in practice. And at the top of the pyramid is wisdom. It answers the fundamental question, why? This is a deep understanding of patterns and principles. For example, understanding seasonal temperature cycles and their impact on the ecosystem, or more pragmatically, planning wardrobe updates according to the season. And now the main conclusion for our course. The job of a modern database is to store data at least at the information level, not just data. The database forcibly requires context. It will not allow you to simply save 10.5. It will force you to put this value into a column named temperature_Celsius and define an exact data type for it. For example, decimal, 4, 1. The very structure of the database is that context which turns data into information. Okay, we figured out data and information. Moving on to the second component, database. The key definition is on the screen. A database is a structured and interrelated set of data. And these two words, structured and interrelated, are crucial. They are what separate a professional database from, for example, a large Excel spreadsheet. Let's look visually. Before you is a typical example of a flat file, a table where we try to store data about students and their academic groups. Everything seems logical, but this simple structure creates three significant problems, known as data anomalies. First is the update anomaly. Imagine that Professor Petrenko, curator of Group CAN 101, changes his last name. To maintain data relevance, we will have to find every student of this group in the table and manually correct this last name. If we miss even one row, that's it, the data has become inconsistent. We lost integrity. Second, even worse, deletion anomaly. Look at Group AI102. It has only one student, Melnick V. If we expel him and delete this row, we will completely lose any information that Group AI102 existed at all, and that association, Professor Kovalchuk was its curator. Data will simply disappear. And third, insertion anomaly. We cannot create a new group, say CAN 103 with curator Professor Tkachenko, until at least one student appears in this group. Because we cannot create a row where the student's name is empty. Our structure does not allow this. This data model is fragile, redundant, and dangerous. And it was precisely to solve these problems that the concept of a database was invented. So, how do we solve these update, deletion, and insertion anomalies we saw? The answer is fundamentally simple. We stop mixing everything into one pile. A real database models the subject area logically, and in the logic of our university, student and group are two different entities. Therefore, we create two separate tables as you see on the screen, the students table and the groups table. And then we establish a logical link between them. And now look how our problems disappear. Update problem. If Professor Petrenko changes his last name, we edit one record in the groups table. That's it. Since all students simply refer to this record, the data automatically becomes consistent for everyone. Deletion problem. If we expel Melnick V, we just delete one row from the students table. The groups table is not affected by this. Information about the existence of Group AI102 and its curator remains in the system. Insertion problem. We can add Group CAN 103, CAN 104, and new groups directly to the groups table, and there may not be any students in them yet. This is the true essence of a database. It is not just file storage. It is a method of logical modeling that eliminates redundancy and guarantees data integrity, thanks to clear management of relationships between them. So we have information, data plus context, and database, logical model that eliminates anomalies. But what actually manages all this? What physically writes data, finds it, protects it? This task is solved by the third component, the Database Management System or DBMS. Simply put, the database is structured storage, and the DBMS is the engine. It is a comprehensive intermediary program that does all the heavy lifting. It receives your commands, manages transactions, ensures security, guarantees integrity, and physically works with files on the disk. There are a large number of different DBMSs based on different models. Within our course, we will focus on two main types. The first is MySQL. This is a classic relational system, SQL, the most popular open-source DBMS in the world, known for its reliability. We will perform all our practical work on it. The second, for contrast, is MongoDB. This is a popular NoSQL system that works not with tables, but with flexible JSON documents. It is perfectly suited for huge volumes of unstructured data and horizontal scaling. Although these systems are ideologically very different, almost all modern DBMSs, including both MySQL and MongoDB, operate on a single architecture. And this is the next thing we have to sort out, the client-server model. We determined that the DBMS is our engine, but how do we communicate with it? Do we just open data files in Notepad? No. Almost every modern system, whether MySQL or MongoDB, operates on a client-server architecture, which you see in this diagram. This means the system is clearly divided into two parts. On one side, usually somewhere far away on a secure server, the DBMS server runs. This is that very engine. It is a background service, a daemon, that is constantly running. This process physically owns the data files. It guards them, manages transactions, optimizes queries. You never interact with it directly. On the other side is the client. The client is any program that knows how to talk to the server, usually over a network. This could be your website backend written in Python, or an administrative tool in the terminal. The client only sends commands, for example, in SQL query, and waits for a response. And this leads us to a key moment for our practice. The MySQL Workbench program which we will use is not the database. It is just one type of client, a convenient graphical user interface, GUI. If the MySQL server is a powerful engine under the hood, then Workbench is our visual steering wheel and dashboard. We use the steering wheel to give commands to the engine, but the real work happens right there on the server. Okay, we know our tools: data, database, and database management system. Now the question: how do we design a database from scratch? Of course, no one sits down and starts writing code to create tables immediately. The professional design process is divided into 3 levels of abstraction. This is a fundamental concept that allows us to separate business requirements from technical implementation. Let's consider this with a simple scenario. The university tells us, we need students to be able to register for courses. How do we turn this requirement into a database? We start at the top with the conceptual level. This is the level where the answer to the question "what" is sought. At this stage, we don't care what server we have, SQL or NoSQL. We care only about business logic. What are the entities here? We have the entity student, and there is the course. What is the relationship between them? One student can study many courses, and one course can be attended by many students. This is a many-to-many relationship. That's it. At this level, the result is simply a relationship diagram and a blueprint of the business process. Next, we move to the logical level, where we try to find the answer to the question, how? How do we technically organize these entities? Here we choose a model, for example, Relational SQL. Our conceptual entities become specific tables, the students table and the courses table, and the many-to-many relationship, which cannot be implemented directly, we resolve by creating a third intermediate table. Let's call it enrollments. The result is a technical plan, a schema of tables, columns, and keys. And only now at the final stage do we move to the physical level, where we answer the question by what means. Here the DBMS, our engine, decides how to physically store these tables on disk. Which data type to choose for student ID int or long? Which type for the name varchar? Most importantly, what indexes do we need to create to instantly find a student by last name, rather than scanning millions of records? These 3 levels are our path from idea to implementation. And the main goal of such separation is what we will discuss next: data independence. So, why do we separate the process into these 3 levels at all? Conceptual, logical, and physical. Why this complication? The answer is one of the most important concepts in design: Data independence. Simply put, we want to be able to change something at one level without breaking everything else. The first type of independence is physical. This means we can completely change how data is physically stored on disk, and not a single line of code in the program using these data has to be changed. For example, a database administrator can move all database files from a slow hard drive to a fast SSD. The program connected to the database won't even notice, it will just start working faster. But the most common example is indexing. And this brings us to the key trade-off in any database: read speed versus write speed. An index is, in essence, like an alphabetical index at the end of a thick book. It incredibly speeds up searching for the necessary information, i.e., reading it in the book. But every time you add a new term to the book, i.e., make a new record, you need to update both the text itself and this alphabetical index. More various indexes mean faster reads, but slower updates and insertions. Physical independence allows the administrator to manipulate this balance, adding or removing indexes to optimize performance, and all this without needing to interfere with the program logic working at the logical level. Physical independence is great for technical optimization, but there is a second, more powerful type that is critically important specifically for business: logical independence. Logical independence is the ability to change the logical structure of our database, i.e., add new data, without breaking applications that already exist and work with this database. Achieving this is much harder, but it is exactly what allows the system to evolve with the business, rather than requiring a complete rewrite every 2 years. Let's look at a classic example. Imagine we have a students table. Version 1.0 contains only ID, name, and average grade. And somewhere in the accounting department, there is an old program that runs once a month. All it does is read student_ID and average_grade to calculate scholarships. Now, a year later, the university administration has a new requirement. We need to store students' contact information for course registration. Our developers go and change the logical model. They add 2 new columns to the students table: email and phone_number. What will happen to the old accounting program? Absolutely nothing. It will continue to work perfectly. Why? Because from its point of view, those 2 columns it needs, student_ID and average_grade, are still in place. It simply ignores the new columns, the existence of which it doesn't even know. This is the power of logical independence. Together, these 3 abstraction levels and 2 types of independence are the foundation for designing systems that will be flexible, scalable, and most importantly, durable. We defined our 3-tier architecture. Now we return to the very beginning, to the highest level, which is also the most important for the architect: conceptual modeling. Its goal is to describe the business logic of the subject area. We don't think about SQL, we don't think about servers or data types. We think only about business. What objects, entities, are in our system and what are the rules, relationships between them. The industry standard for this is the ER model, entity relationship. It is, in essence, a graphical language. Historically, the first was Peter Chen's notation. You see an example of it. It is very pure academically. Rectangles for entities, diamonds for relationships, and each individual attribute is a separate oval. This looks logical, but imagine a real system with dozens of entities and hundreds of attributes. This schema would turn into chaos with thousands of ovals. It is simply impractical. Because of this, today in the industry and in all modern tools, the crow's foot notation dominates. The reason for its popularity is information density. Look at how much more compact it is. Attributes are neatly listed inside the entity rectangle, and all the complex relationship logic, one-to-many, one-to-one, is encoded by small symbols at the ends of the lines, which look like a crow's foot. It is this notation that we will study and use moving forward. Okay, we chose our notation, crow's foot. Now we need to learn the grammar, i.e., the language this notation describes. The ER model itself is, in essence, the grammar of data description. Like any language, it consists of 3 main conditional parts of speech. First, we have the entity. This is our conditional noun. This is the main object, item, or concept about which we want to store information. For example, student, course, lecturer. Second, we have the attribute. This is our conditional adjective. An attribute does not exist on its own, it always describes a noun. For example, surname, first name, or date of birth are conditional adjectives describing our noun student. And third, we have the relationship. This is our verb. Verbs connect nouns to build a meaningful sentence. Relationships connect entities. For example, student, noun, belongs, verb, to a group, another noun. This is the entire conceptual model. Nouns, adjectives, and verbs. To learn how to build complex and correct sentences, i.e. data models, our next step is to analyze each of these parts in detail. And we will start with the entity. So, starting the review of the first component of the conceptual model, the entity. What is it? It is simply a class of objects or concepts about which we want to collect information. These can be physical objects like student or car, or abstract concepts like course or project. If student is an entity, i.e. a class, then specific student Serii Bondarenko is an instance of this entity. But the main question we must ask during modeling: can this object exist independently? This divides all entities into two types, strong and weak. Most entities are strong. Student exists on their own. Course exists on its own. They are independent and have their own unique identifier. But there are weak entities. A weak entity cannot exist without its owner entity. A classic example you see in the diagram is invoice and invoice line. Invoice is a strong entity. It exists on its own, has a number, date, client. But what is an invoice line? It is a record like product A, 2 pieces, 50 hryvnias. Does this record make any sense without the invoice to which it belongs? Absolutely not. It cannot exist independently. Its existence depends entirely on the owner. This is a weak entity. So we defined our entities. Now we need components that describe them. These are attributes. An attribute is simply a property of an entity. If our entity is student, then surname, first name, and date of birth are its attributes. They provide details. But attributes are not monolithic. During design, we must classify them, as this will directly affect how we build our tables. There are 3 main classifications. On this slide, we will consider the first 2. First, by complexity. An attribute can be simple or atomic, meaning it cannot be divided further. For example, date of birth is a single whole, or it can be composite. A classic example is address. Address is actually not one field. It is a composition of street, city, and postal code. In design, we almost always break composite attributes into simple ones. Second classification, by number of values. Most attributes are single-valued. A student has only one date of birth, or one record book number. But some attributes are multi-valued. One student can have, for example, 3 different phone numbers, or know 4 foreign languages. And these multi-valued attributes create a specific problem for classic relational SQL databases. SQL tables are built on the idea of one value in one cell. We cannot simply shove a list of 3 phones into one cell. This requires a special solution which we will consider on the next slide, along with the third classification of attributes. We continue the analysis of attributes. The third, final classification is derived and stored attributes. Most attributes you see are stored. We physically store surname or date of birth in the database. But some attributes are derived. This means their value is not stored on disk, but is calculated on the fly during a query. A classic example is age. We store date of birth. This is a stored attribute, but age itself, we calculate instantly when we need it. Why don't we store age? Because it is bad practice leading to update anomalies. If we physically stored the student's age, we would have to run a process every night at midnight to update the age for those who have a birthday today. If this process breaks, our data becomes incorrect. It is much safer to simply calculate it. In diagrams, as you see in the example, derived attributes are marked with a /age. Now look at this diagram more closely. It also shows the standard solution to that multi-value problem we talked about. How to store multiple phones? Answer: we do not try to shove the list into one cell. We use normalization. We move phones into their own separate weak entity. You see it student_phone. This entity is linked to its owner, student, by a one-to-many relationship. Now, if a student has 3 phones, we simply have 3 separate records in the student_phone table, each referring to this one student. This is a clean, correct relational approach. So we have our entities and attributes, but a fundamental problem arises. How do we guarantee distinguish one instance from another? For example, we might have 2 students Bondarenko Serii with the same date of birth. How does the system understand who is who? For this, every entity must have a key. A key is an attribute, or set of attributes, that guarantees the uniqueness of each record. In our diagrams, we mark it as PK or primary key. When choosing this key, engineers have 2 paths. The first path is to use a natural key. This is an attribute that already exists in the real world and is, supposedly, unique. For example, passport number, or taxpayer identification code. This sounds logical, but in practice it creates many problems. What if the student hasn't received a passport yet? What if the number changed? Natural keys often turn out to be unreliable. Because of this, in modern design, the second approach dominates, the surrogate key. This is an artificial key. We simply add a new attribute to our entity, usually just a number student ID, and its sole purpose is to be a unique identifier 1, 2, 3, 4. It has no business meaning, but it guarantees uniqueness, will never change, and is extremely effective. This is the de facto industry standard. Starting a detailed review of the last component's relationships, we will consider 3 types of cardinality. The first and simplest is one-to-one. As the name implies, this means that one record in table A can be linked to only 1 or 0 record in table B, and vice versa. A classic example is student and student ID card. One student has one card. One card belongs to one student. In fact, this is quite a rare relationship. After all, a logical question. Why don't we just add card_number as a regular attribute column to the student table itself? Answer: we use a one-to-one relationship when we have good reasons to separate data. For example, student ID data may contain sensitive information, e.g., chip data for access, and we want to move them to a separate table with different security settings. Or perhaps we need the main student information constantly and card data extremely rarely, and we don't want to burden the main table. As you see in crow's foot notation, this relationship is marked by 2 vertical dashes on both ends of the line. If the one-to-one relationship was quite rare, now we move to the workhorse of any relational database. This is the one-to-many relationship. Probably 90% of relationships you will design in your career will be of this type. The logic is simple. One instance from the parent side can have many related child instances. But, and this is very important, each child instance can be linked to only one parent. The classic example we return to: one group has many students. Group CAM 101 can have 30 students, but each specific student, for example Bondarenko, can belong to only one group. It is this relationship structure that allowed us to solve those data anomalies we saw earlier. In crow's foot notation, we mark this clearly: a vertical dash on the one side group, and a crow's foot symbol on the many side students. This solves most of our tasks. But one question remains: what if logic requires many on both ends? We have approached the final, third type of relationship, many-to-many. It describes very common situations in the real world where many on one side is connected to many on the other. The classic example we already mentioned: students and courses. One student can register for many courses, for example, databases, mathematics, and English language. At the same time, one course, e.g. databases, is attended by many students. Conceptually, on our ER diagram, we draw this honestly: a crow's foot on both sides, as you see in the image. But, and this is one of the most important moments in all relational design, such a relationship cannot be implemented directly. In the relational model, there is no mechanism to physically connect 2 tables with a many-to-many relationship. This means that every time we find such a relationship in our conceptual plan, we identify a problem. This is a red flag telling us this relationship must be resolved before we can move to the logical level. And exactly how we resolve it is the topic of our next slide. So we have a problem. We cannot directly connect tables with a many-to-many relationship. How does SQL solve this seemingly unsolvable task? The solution is standard, and you will use it constantly. We resolve this relationship. We break it by creating a third, intermediate entity. It is often called an associative entity, or simply a join table. Look at the diagram. Instead of one bad M relationship between student and course, we create a new entity in the middle, course registration. And this new entity turns our one impossible relationship into two perfectly legal, one-to-many relationships. One student now has a one-to-many relationship with registrations. That is, one student can have many registrations for different courses, and one course also has a one-to-many relationship with registrations. One course has many registrations from different students. This intermediate table registration now stores all facts. Each row in it is simply two identifiers, student ID and course ID, which essentially means student 5 is registered for course 10. Student 5 is also registered for course 12. This is a clean, efficient, and the only correct way to implement M relationships in a relational model. Okay, we just completed the full development cycle at the first conceptual level. We have our ER diagram. We know our entities, attributes, keys, and all relationships. We have an ideal business plan for our system. Now we must descend to the second level, logical. The goal of this level is to translate our abstract conceptual plan into a specific technical language that our engine, our DBMS, will understand. And here in modern design, we find ourselves at a fundamental crossroads. We have to make the main architectural choice between two completely different philosophies of working with data. Path A is the classic dominant approach, relational model or SQL. This path puts strictness and data integrity above all else. It requires a clear schema, normalization, i.e. elimination of any duplication, and guarantees integrity through so-called ACID transactions. Path B is the modern alternative, NoSQL, or not only SQL. This philosophy was born from the needs of web giants to process petabytes of data. Here the priorities are different. Flexibility, ability to add data without a clear schema, and horizontal scaling, ability to simply add new servers to increase power. The choice between these two paths determines the entire future architecture of your system. Let's look closer at path A first. So let's take path A. This is the relational model or SQL. This is the classic, most widespread, and frankly speaking, dominant approach to data management in the industry for the last 40 years. All its logic is based on the mathematical concept of relation, but it is enough for us to know its physical embodiment. It is a regular table. Everything in the relational model is tables consisting of rows and columns. The main advantage of this approach is very clear, strict rules for translating our conceptual ER diagram, which we just drew, into a logical model. The rules are very simple. Every entity becomes a table. Drew a student entity, got a students table. Every attribute in this entity becomes a column in that table. Attribute surname, got a last name column. Relationships are implemented using foreign keys. That is, for a one-to-many relationship group -student, we simply add a group ID column to the students table. And as we just analyzed in detail, every many-to-many relationship becomes its own intermediate table. This is a very clean engineering transformation. Examples of such systems you probably know or have at least heard of. You all know Oracle, Microsoft SQL Server, and of course MySQL, which we will study. But why is this model so powerful? Why does it dominate? This is determined by its three key aspects, which we will consider next. So, we know how to turn our diagram into a set of tables. But why has this model dominated the industry for over 40 years? Why do all banks, financial, and telecommunication systems run on it? The answer lies in three fundamental components or aspects of this model. First, the structural aspect. It is simple, everything is a table. No complex pointers or hierarchies visible to the user. Only tables, rows, and columns. Second, and most importantly, is the integrity aspect. The relational model is strict. It forces us to define data types, it guarantees key uniqueness, It uses foreign keys so you physically cannot create an orphan record, e.g., a student referring to a non-existent group. This strictness gives us the gold standard of reliability, ACID transactions. We won't delve deep into this now, but briefly, ACID is a set of guarantees that your operation, e.g. transferring money from account A to account B, will either happen completely and correctly, or not happen at all even if the power goes out in the middle of the operation. That is why banks use SQL. Third, the processing aspect. And this is the genius of the model. Interaction with data happens declaratively, using the SQL language. What does this mean? It means you tell the database what you want, not how to do it. You simply declare, give me the surnames of all students in group CAN 101 with an average grade above 90. You do not write a loop, do not open files, do not iterate through records manually. The DBMS engine decides itself how to execute your query most efficiently. It is this model that is the foundation for normalization, a formal process that we intuitively performed when resolving flat file anomalies. We just saw Path A, the structured, strict, and reliable world of SQL. But what if our priorities are completely different? This leads us to Path B, non-relational or NoSQL models. The abbreviation stands for not only SQL, and this is not one product, but a whole family of completely different approaches to data storage that rejected the strict rules of the relational world. Why did they appear at all if SQL is so great? They were born from the limitations of SQL when it faced the problems of web giants Google, Amazon, Facebook. There were three limitations. Scale. SQL scales vertically. You buy one but very expensive and powerful server. NoSQL is created for horizontal scaling. You simply add hundreds of cheap servers to process petabytes of data. Speed. SQL is a generalist. Some NoSQL systems are created for one but ultra-fast task, for example caching. Structure. SQL requires a clear pre-known structure. NoSQL thrives where data is unstructured or semi-structured. For example, JSON objects, user comments, metrics from millions of IoT sensors. And this leads us to the main philosophical difference, working with data schema. SQL uses the schema-on-read principle. You are obligated to first clearly define every table and every column, and only then can you write data. The schema is a strict contract. Many NoSQL systems, especially document ones, use the schema-on-read principle. This is a dynamic schema. You have a collection, similar to a folder, and you can simply put a JSON document there with new fields that did not exist before. The database will not complain. It is already the job of your application when it reads these data to figure out that some documents have new fields and old ones do not. This flexibility gives the developer a new, powerful choice that does not exist in SQL, and we will consider it next. So, the key philosophy of NoSQL is flexibility. And this flexibility immediately presents us with a main architectural choice that strict SQL does not give us. This is the choice: embed or reference. Let's take a classic example. We have a blog post and comments to it. This is a pure one-to-many relationship. In SQL, we have no choice. There will be two tables, posts, comments, with a foreign key. But in document NoSQL like MongoDB, we have two paths. Path 1. Embedding, also known as denormalization. We simply take all comments and embed them as an array of JSON objects inside the post document itself. One post. One large document containing both the post and all its comments. The advantage is obvious. Incredibly fast reads. To display the page, we need only one query to the database to get one document. No joins. Disadvantage. This creates data duplication, and if we need to update one individual comment, it becomes a complex operation because it is buried deep in another document. Path 2. Referencing or normalization. This is, in essence, the SQL path. We create two separate collections, analogs of tables, posts, and comments. And inside the post document, we store only an array of IDs of these comments. Here the trade-off is reversed. Updating comments is now easy, they are separate small documents, but reading becomes slower. To show the page, we now need to make two queries. First, get the post and list of comment IDs. Second, give me all comments whose IDs are in this list. There is no correct answer here. It is always an engineering trade-off that depends on what is more important to you: read speed or ease of data updates. And finally, concluding the conversation about NoSQL, it is important to understand that NoSQL is not one specific database. It is a whole family of completely different systems, each created for its narrow task. First, these are document-oriented systems. This is exactly what we discussed: flexible JSON documents. The main player here is MongoDB. Second, the simplest model, key-value. Imagine a giant dictionary or hash map. You have only a key and a value, some block of data. No more structure. Since it is so simple, these systems are incredibly fast. Their main application is high-speed caching. The most famous example is Redis. Third, heavy artillery, wide column databases. These are systems like Cassandra. They were created with one goal: to store petabytes of data, guaranteeing that the system will never fall, high availability, and will not have a single point of failure. Example, Cassandra. And fourth, a completely separate category, graph databases. Their uniqueness lies in that they are optimized not for storing data itself, but for storing and analyzing relationships between them. They are created to instantly answer questions. What is the shortest path between user A and user B? Or what do all friends of my friends have in common? This is the technology behind social networks and recommendation systems. Example, Neo4j. We just finished our review of modern logical models, SQL and NoSQL. But to truly appreciate why the relational model SQL became such a revolution, we need to quickly look at what was before it. In the 1960s and 70s, the hierarchical model dominated. As the name implies, it organizes data in the form of a strict tree. The best modern example you see every day is your computer's file system. One folder can contain many files, but each file lies in only one folder, or the Windows registry. The entire model is based on the parent-child relationship, and one golden unbreakable rule applies in it: each child can have only one parent. This works great for describing one-to-many relationships, but the model fails completely when trying to describe a many-to-many relationship. And what if a child must have two parents? For example, our student and course example. A student studies many courses, and a course has many students. The hierarchical model is unable to describe this logic. It was this problem that led to the emergence of the next model. So the hierarchical model failed because it couldn't handle many-to-many relationships. In the 1970s, it was replaced by the network model. Its innovation was simple but powerful. It abolished the one-parent rule. As seen in the diagram, in the network model, any child object could have multiple parent objects. And just like that, the M problem was solved. This model was much more flexible and dominated large industrial systems of that time. But it had a fatal flaw. A problem so serious that it led to the creation of SQL. This flaw is the complete lack of data independence. In the network model, program logic, i.e., the code written by the programmer, was rigidly tied to how data physically lay on the disk. The program had to know the exact access path to the data. What did this mean in practice? It meant that if a database administrator wanted to simply optimize storage, for example, add a new index or change the file linking method so everything worked faster, this required a complete rewrite of every program that worked with this database. Systems were incredibly fragile and astronomically expensive to maintain. And that is exactly why the relational model, SQL, became a revolution. Because its main promise was the one we talked about earlier: data independence. Clear separation of the logical level, what the program sees, from the physical, how data lies on disk. This allowed optimizing disks without touching the code, and this solved the main problem of network databases. We have come a long way today, from the basic definition of data to historical models of the 70s. Let's summarize the key points to take away from this lecture. First, we laid the foundation and now clearly distinguish the main concepts. Data are raw facts, database is a logical structured model that solves anomalies, and DBMS is the software engine that manages this model. Second, we have a design roadmap. We know that any design moves through 3 levels of abstraction, from conceptual, business idea, to logical, technical plan, and to physical implementation on disk. Third, we studied in detail the basis of the first conceptual level, the ER model. We know what entities, attributes, keys are, and most importantly, how to model three types of relationships, one-to-one, one-to-many, and how to correctly resolve many-to-many relationships via an associative entity. And finally, we saw that at the logical level, we have a fundamental choice. We can go the classic relational SQL path, which prioritizes data integrity and reliability, ACID, or the modern NoSQL path, which prioritizes dynamic schema flexibility and massive horizontal scaling. And in conclusion, a few key questions for self-check. I would like you to definitely be able to clearly answer them when preparing for the next topic. First, can you now explain the fundamental difference between a database as a logical model and a DBMS as a software engine? Second, do you understand the design roadmap, why we need 3 levels of abstraction and what is the goal of each? And third, can you formulate what is the main philosophical and technical difference between SQL and NoSQL in terms of working with schema and relationship implementation? These are just 3 questions for focus. The full list of control questions for self-check is provided in your lecture notes. In case of additional questions, you can contact me at the email address indicated on the screen. Thank you for your attention. This concludes the first lecture.